Lab 2 Magnetic Field of a Bar Magnet for Physics 2212. So for the introduction, the goal of this lab is to measure the distance of a magnetic field and see how distance relates to the magnitude of the magnetic field. This will be based off a field from a dipole bar magnet. Then we will use a computational model to compare our experimental results to our calculated results to see how accurate they are. This lab includes several physics concepts such as the Biot-Savart law that helps calculate the magnetic field. Our results from the lab include that the distance dependence is negative 3.0035 meters and the value of the magnetic dipole was 2.606 amperes meters squared. So some observations that I made were that when the magnetometer is far from the magnet, it measures a magnetic field near zero in the x direction, and also as the magnetometer moves closer to the magnet, the measured x component of the magnetic field changes and increases. So in this experiment, I calibrated the magnetometer, then I found the distance from the magnet to the magnetometer by using the x component values. Based off of this data, I used the magnetometer to find the other components, and then I found the perpendicular distance and the off-axis magnetic field and the magnitude of the net magnetic field. So on the right is my data from my on-axis magnetic field measurements, and on the bottom my perpendicular axis measurements. From this, I got the experimental perpendicular distance to be 0.1797 meters, and that the magnetic field at 45 degrees is negative 1.65 e to the negative fourth, 5.066 e to the negative fifth, and negative 3.757 e to the negative sixth as a vector. Then on the left is my graphed and fitted data from the on-axis measurements that I will show how I use to calculate the dipole moment of the magnet. So using the slope of the graph and the distance-dependent equation, I got that n equals the slope value, which is negative 3.0035, and the ln of k equals negative 14.467. And using the equations on the slides, I got that k equals 5.212 e to the seventh, and that the b bar equals 5.212 e to the seventh. And using this value and the dipole equation, I got that the dipole moment of the magnet is equal to 2.606 amperes meters squared. So here is my glow script code. On the left, you can see that my function for the calculated magnetic field. This creates the magnetic field due to a dipole at different locations and orientations. On the right is where I constructed the arrows that represent the perpendicular on-axis magnetic field by using this function. Then I calculated the magnetic field at 45 degrees by using my measurements from the lab to compare to my experimental values. And here is my computational model. You can see that the green arrows denote the perpendicular field, the purple arrow denotes the 45 degree field, and the orange arrow represents the on-axis magnetic field. From this, I got that the distance was 0.25413 meters, and the magnetic field at 45 degrees is 7.95 e to the negative sixth for the x component, 2.38 e to the negative 5 for the y component, and 0 for the z component. So comparing my computational values to my old values, the distances are fairly similar, but the magnetic fields were different. The computational model gives a more accurate estimate of what the actual magnetic field is. So now to answer some final questions. If in the experiment I oriented my setup so as to compensate for magnetic north, what if I hadn't done that and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? My results would have changed because by using magnetic north, the x component is 0. This means only one field is being measured, and without ensuring this, the results would be different, as we will be accounting for a different x value of Earth's magnetic field, and the x value would not be 0. All of the values would be much less accurate. So The next one, now imagine if I had two identical magnets. If I redid the experiment, but instead of using a single magnet, I used two identical magnets stuck together end to end. The measurements would likely double in magnitude, but would definitely be more than the current value. Thank you.